Good afternoon, everyone. Thank you all for being here. My name is Minna from ASHRAE Falcon Chapter, and I'd like to welcome you to our webinar. We're very delighted to have you with us today, and we're looking forward to an informative and interesting session on the improvement of energy efficiency in air-cooled screw chillers. Firstly, I'd like to take you through the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflicts of interest. Just a quick disclaimer before we start our presentation. Information contained within this presentation is presented by ASHRAE Falcon Chapter as a supplier or stakeholder webinar. It presents information of current interest and to provide a venue for interaction between ASHRAE Falcon Chapter members, the different industry stakeholders, and the webinar presenter. These webinars should not be considered peer-reviewed or the final word on any subject. ASHRAE Falcon Chapter has not investigated, and ASHRAE Falcon Chapter expressly disclaims any duty to investigate any product, service, procedure, design, or the like, which may be described herein. The appearance of any technical data or editorial material in this presentation does not constitute endorsement, warranty, or guarantee by ASHRAE Falcon Chapter for any product, service, procedure, design, or the like. And let me remind you that we will be recording this webinar and uploading it to the ASHRAE Falcon Chapter YouTube channel. If you'd like to download the presentation that's going to be used for this webinar, you can do so from the handouts. If you're using your mobile phone, click on the handouts button on the top right corner of your screen to download the presentations. And we'll be having a live Q&A session at the end of the question panel, or at the end of the webinar, where we will receive your questions, which you can send through the question panel or question button. So please send your questions as the webinar is going on, because at the end the speaker is going to be answering them. Without further ado, it's my pleasure to introduce Mr. Saeed Al-Laham, our speaker for today, who is a strategic accounts leader at Train. Mr. Saeed, I'm going to leave the floor to you now, so please.
Thank you, Mina. Thank you, Mina, for the introduction. Thank you all for your time and efforts attending today's webinar. I hope you and your families are all safe. I would like to thank ASHRAE Falcon Chapter for their leadership and efforts in organizing these webinars. I am Saeed Al-Laham, Strategic Accounts Leader in Train. Before joining Train, I worked in Canada as a design engineer for HVAC equipment. I joined Train in June 2009 in Train UAE. And since that time, I enjoy working with consultants and design engineers to develop innovative solutions that are energy efficient and environment sustainable. Our topic today is opportunities of energy efficiency in air-cooled chiller. Our outline today is understand the importance of reducing energy intensity of the world, have introduction to the air-cooled screw chillers, components, and available technologies, and relate that one to the options available with heat recovery heat pumps and related to the building's energy efficiency, and finally, summary and conclusion. I will stop the camera now so that we can focus on the content of the presentation. Most of the world organizations have sustainability goals. For example, the company I work for, our objective is to reduce our customer carbon footprint by 1 gigaton in the next 10 years. Emission of greenhouse gases such as CO2 is responsible for the global warming. There are two types of emissions of carbon footprint or carbon footprint. First type is direct, that is related to the leak refrigerant leak to the atmosphere. We made seminars before about the new generation refrigerants and the low GWP, global warming potential, so we will not talk about it today. Maybe we can arrange a separate webinar in the future for this topic by itself. The second type is indirect emission, which is related to the energy consumption coming from the power generation in the plants. It is estimated that every kilowatt hour of power generation is equivalent um, 47% of the world greenhouse gas emissions are responsible from the buildings. 49% of the world energy use comes also from the buildings, residential, industrial, and commercial buildings. This is considerable percentage of the world energy consumption. So any little saving that we make in the building energy consumption is important. In the last decade, we started hearing more about the net zero energy buildings and the carbon neutral buildings. Reducing energy intensity is paramount because it means reducing the greenhouse gases and emissions, which is reducing the carbon footprint. So we take every opportunity to maximize the building energy efficiency. For example, if we can select a chiller which is more efficient with a COP of 3.1 instead of 2.8 COP. But this approach has limitation. Another approach is to have holistic approach to the building systems. For example, looking to the building chilled water system and domestic hot water systems, and see opportunities how we can combine the needs from the chiller and maximize the utilization of the chiller in both applications. Let's start by understanding the air-cooled screw chiller. The air-cooled screw chiller main components are compressor, condenser, the condenser coil, the condenser fans, the control panel, the starter, the panel and the casing, condenser fans, compressor, refrigerant piping and accessories, and the oil separator. Let's start by the compressor. Compressor is the heart of the chiller. Compressor keeps pumping the refrigerant from the low pressure to the high pressure. The compressor we see here is a twin screw type. We see here the motor terminals. We see here the rotors. We see here the stator. And we see here the helical rotors, the oil filter, and the bearings. As we see here, the motor is two-pole motor, so its speed is 3,000 RPM, which is directly coupled to the motor, so the compressor speed is 3,000 RPM. The helical rotors are optimized for design of refrigerant R134A, and in the last few years, we started also using refrigerant R1234ZE, which is an HFO refrigerant with a low global warming potential, and it has wider operating maps. So the compressor rotors are optimized for both R134A and R1234ZE. Compressor construction can be hermetic or semi-hermetic. Hermetic means that we don't have access to the internal bars. This is used in smaller size compressors, such as in appliances at home. For large compressors, we have semi-hermetic construction, where we can have access to the construction and the internal parts of the compressor. And the compressor is cooled by refrigerant coming from the evaporator, which is coming through the motor, cooling the motor before being compressed in the compressor. The oil and refrigerant tends to leave the compressor. We separate the oil in the oil separator, as we will see in the next slides, and the oil is returned to the compressor to maintain the combustion tightness and combustion efficiency, and to prevent the wear and tear between the male and the female rotors. As you know, most chiller manufacturers used reciprocating compressors before, but reciprocating compressor has many moving parts, so it has less reliability. So the less moving parts we have, the less chance of failure and the better reliability we have. There are two types of screw compressors available in the market. One is screw compressor we see here, and single screw compressor. It uses one single screw and two gate rotors. Crane evaluated the direct drive twin screw compressors in the 50s and found it to be the most reliable compressor. In that time, it was not feasible to make a twin screw compressor because it needs fine machining and it needs 4-axis CNC machining. Till 80s, when there was a revolution in the computer science, where CAD and CAM started to be used more widely. It enabled manufacturing of these helical rotors using 4-axis CNC machinings. These rotors are made from steel, which is sized for the lifetime of the compressor. And the impact of the speed of the compressor lifetime, the compressor is running at 3000 RPM. As we increase the speed of the compressor, it increases the compressor efficiency, but that will increase the wear and tear between the male and the female rotors. The chiller capacity control. Chillers are designed to work at full load and part load as well. As delta T between entering and leaving water changes, or water flow rate changes in the case of variable flow, the controller will send signal to increase or decrease the capacity of the chiller. That includes refrigerant flow in the circuits, compressor expansion valves and condenser fans, etc. Normally, chillers are equipped with multi-compressors. Some chillers are equipped with 2 or 3 compressors or 4 compressors. In general, the more number of compressors per chiller, it will be easier to control. Also, the slide valve mechanism is very common technique for the capacity control. It is a sliding valve that controls the refrigerant flow. Slide valve is more efficient in capacity control, especially in high percent loading, such as 70 or 80% of the compressor loading. Variable speed drive is also common. It controls the output frequency and hence controls the compressor speed. Variable speed drive is more efficient in the lower percentage loading of the compressor, such as 30% or 40%. Manufacturers use various techniques, so it may be difficult to specify one technology or one type for the capacity control. It is recommended to specify the required output, which is the IPLV. We come back to the oil separation. Remember, we said that the oil and refrigerant mixture leaves the compressor, and we want to bring back the oil for the rotors to keep proper lubrication in the helical rotor. The oil separator is a device where we have the oil and refrigerant mixture coming here, and the refrigerant is separated, continuing to the condenser, and the oil is collected in the bottom and returning to the compressor. In the high ambient application, the oil needs to be cooled further before returning to the compressor in order to maintain its viscosity. So we come now to the evaporator. We spoke about the compressor and the oil circuit. We come now to the evaporator. The evaporator is a heat exchanger where refrigerant evaporates and the water flows. It gives its heat to the refrigerant to get colder. There are different types of evaporators, such as brazed plate heat exchanger and shell and tube evaporator. The one that we see here is shell and tube. The shell is made from steel and the tubes are made from copper. The evaporator can be 2 or 3 circuits or 1 circuit. We see here 2 circuits. Evaporator types can be flooded type, or direct expansion, or falling film. In the direct expansion, we have the water flowing in the shell and the refrigerant flowing in the tubes. The advantage of the direct expansion, or the classical DX, is that it has a small refrigerant charge, but the problem, the efficiency is low. The flooded type evaporator, it uses refrigerant, which is flooded in the shell, using a ball valve to control the liquid or the refrigerant liquid volume in the evaporator. 1/3 and the 2/3 is vapor. The flooded type, it has excellent heat transfer efficiency, but the disadvantage is it uses large refrigerant charge. ASHRAE patented the falling film evaporator, which is a hybrid of the DX and the flooded type. So it's using electronic expansion valve to expand or throttle the refrigerant in the shell, not in the tubes, and the water is flowing in the tubes. The electronic expansion valve is a device which is used to control the refrigerant flow, which is the refrigerant is coming from the liquid line with high pressure, and it's throttled in the evaporator to expand. Before using the electronic expansion valve, TXV or the thermostatic expansion valve was used. But with the advancement in the microprocessor and the electronic expansion valve, it is more stable and accurate to control. It also has fast response, so it saves more energy. We come now to the condenser. The condenser is the condenser coil and the fans. Condenser is a heat exchanger of the coil and fan. Refrigerant flows as superheat gas. It is desuperheated, then condensed to liquid, and then subcooled. The amount of heat rejected to the ambient equals the cooling capacity plus the work done by the compressor. We see here the microchannel type of the coil, and we see here the copper tube aluminum fins. Every heat exchanger, it has its pros and cons, but heat exchanger or the microchannel heat exchanger is becoming more popular in the last years. The condenser fans motors can be AC type or EC type. And finally, we come to the controller. The electric and control panel includes the starter, electrical wiring, and the microprocessor. Microprocessor is the brain of the chiller. It is DDC, where it stores the intelligence of the algorithms in the DDC controller. It controls the chiller operation to meet the chilled water temperature. It controls the fans, the motor, the electronic expansion valve, the compressor start and stop, etc. It also provides safety and protection for the chiller and for the compressors, such as antifreeze and phase imbalance. Microprocessor has user interface, which allows operator to make settings, such as setting the leaving water temperature, and to view data and trends and graphs, and to view the alarms, and finally also to generate reports. And microprocessor should be able to communicate with external chiller plant manager or building management system. So we had an idea about the components of the chiller. So we look to the chiller as a device where it consumes electricity. It uses power to generate cooling, which is the useful energy. So the energy efficiency ratio is the cooling capacity divided by the power input of the chiller. And the heat which is generated in the condenser here is rejected to the ambient, which is being wasted. IPLV gives 1% importance to the full load at 95. Remember that these figures are just metrics to compare the individual chillers. In the real life, it is important to look to the system and the annual energy consumption of the whole system. For example, if we have more chillers in the system, like 3 or 4 chillers per chiller plant, the weight of the energy efficiency ratio, EER, the full load, it becomes more important than the IPLV. Now we come to the option of the heat recovery. We have here a chiller, and as we said, the chiller is providing cooling, so the cooling load. And instead of rejecting the heat, now we are using the hot water for useful purpose, for example, for the domestic hot water or for any other energy consumption for using the hot water. So the total energy consumption, total energy ratio is cooling capacity plus heating capacity divided by the power input. There are 2 types of heat recovery. First one is partial heat recovery. We have brazed plate heat exchanger, which is connected in series with the compressor and in series with the condenser. The hot gas leaves the compressor as superheat. It gets desuperheated here, and the surplus of heating is continuing to the condenser. That heat, which is recovered from brazed plate heat exchanger, goes to the meeting the heating load. This process is not controlled process, so we recover here whatever is possible, and the maximum capacity is 25% of the cooling capacity. For example, if we have here an air-cooled chiller, its cooling capacity is 681 kilowatt, and the power input is 218 kilowatt. The energy efficiency is 3.12 If we select a chiller with partial heat recovery option, it will give cooling capacity of 677 kilowatt, heating capacity of 169 kilowatt, and the power input is 2024. So the total energy efficiency is 3.77. The other type of heat recovery is total heat recovery. In each refrigerant circuit, we have raised plate heat exchanger connected in parallel with the condenser. In each circuit, we have a three-way valve to control the operation mode. In the chiller mode, the refrigerant will flow in the condenser. And in the heat recovery mode, the refrigerant will flow in the heat exchanger, and we recover the heat and we use it for the heating load. The heat recovery capacity is about 130% of the cooling capacity. And of course, the total heat rejection price is more expensive than the partial heat rejection, because partial heat recovery, because we use here two heat exchangers, one per circuit, and bigger size heat exchangers. So this is here an example. We have here air-cooled chiller, cooling capacity 681, power input 218 with 3.1 AER. With the total heat recovery, we can recover 848 kilowatt in heating, so the total energy efficiency ratio is 8. So this is here what we meant by the opportunities to improve the energy efficiency from the same device. So here we are, instead of using 3.1 ER, the energy efficiency now is 8. So if we have, for example, commercial or residential or industrial building, we have here two air-cooled chillers. Every air-cooled chiller is having 150 tons selected at 46 ambient, said water temperature 7 and 12. At the design condition, the chiller power input is 225 kilowatt. And we have hot water system, which is separate. It is estimated to have 500 kilowatt in heating in the winter time and 250 kilowatt in the summertime. And as you see here, the heat is being rejected to the ambient. If we select a chiller with partial heat recovery, and we assume we need 100 ton in the winter time, then we can save 88 kilowatt. If we select a chiller with total heat recovery option, we can save 400 kilowatt. Now, heat recovery alone may not be enough to meet the building load hot water demands. So whatever we can recover from the chillers is good, and it will save energy, and the remaining can be fulfilled by electric calorifier or by solar heating. Using heat pumps for domestic hot water is increasing trend in the last few years. The sources of heat for the hot water can be boilers or fossil fuel, or it can be electric. Remember, for when we are using electric heating for generating hot water, as in the case of electric calorifier, every 1 kilowatt of heating, it needs 1 kilowatt of electricity approximately. The other source is renewable energy, such as solar, which is of course a good solution. But of course, it has limitations because we have sometimes limited roof space, and we have sun available also in limited times. Another technology that enabled the extension of using the renewable energy is the heat pump. Now, in the heat pump, for every 1 kilowatt of electricity, we can generate 3 kilowatt of heating for the domestic hot water. So heat pump, it enables us also to recover the renewable energy and the heat in the air, which is heated by the sun or in the water. Two types of the heat pump by the source of the heat, which is recovered. It can be air source or it can be water source. This is an example using the heat pump. We have here a heat pump, which is connected in series with the chillers. So it has preferential loading. So as the water temperature passes here first, it gets pre-cooled, and that will minimize the cooling load in the air-cooled chillers. Here in the heating system, we have the heating system in series. So the first system gets heated by the heat recovery, and then it can be heated further using the heat pump. This is here a computer selection of a heat pump. So here, as we see, the total power is 100 kilowatt. So by using 101 kilowatt of power input, what can we get? We can get 168 kilowatt of cooling, and we can get 275 kilowatt of heating. So this maximizes the utilization of the equipment and the device that we have. With 100 kilowatt, instead of getting 275 kilowatt only, or getting 168 kilowatt only, we are getting 439 kilowatts. So the energy efficiency ratio is 4.39. It is advisable to make the selection of the equipment or the design to be modular and scalable. That is easy capacity addition and building load or demand increases. And will also optimize the plant efficiency through the control of multiple units by selecting smaller size heat pumps. So for example, instead of using 100-ton heat pump, it's recommended to use 2 heat pumps, each one is 50 ton. We see here another example. We have here a building with 3 water-cooled screw chillers, providing cooling for the comfort cooling, and the condenser heat is rejected to the ambient using the cooling pipes. So all of the heat is rejected to the ambient, and we are using here lots of water. Now, if we use the heat pumps to recover the heat from the water-cooled condensers, we recover whatever heat for the domestic hot water, then we can minimize the water and consumption, and we can minimize the power consumption. So in summary, there are opportunities to enhance the energy efficiency by considering the whole systems of the building, by combining cooling and heating system, not looking to the cooling system as separate from the heating system. And the conclusion is that partial and total heat recovery options are available in the market. It provides simultaneous cooling and heating in the air-cooled chillers, and it helps us to improve the energy efficiency. Heat pumps can also be used to provide either cooling or heating. Heat pumps can be air source or water source, and it is advisable to select smaller size heat pumps or chiller to allow for modular construction to allow for better control. Heat pumps also helps us to extend the usage or utilization of the renewable energy. And finally, we need to think systems, not only think equipment. For example, if we think chilled water system, we can think the impact of the size of the pumps and higher delta T to look for the whole energy system, energy efficiency of the system. Another example of utilization of the energy efficiency is using the ice thermal storage, where we can reduce the total power consumption. So our objective in the end is to reduce the energy intensity of the building and reduce the energy intensity of the world. By this, I come to the end of my presentation. Thank you all for your time and for your patience, and we will come to the questions and answers session.
Thank you, Mr. Saeed. We will now move on to the Q&A session. We've received a tremendous amount of questions, and so we'll do our very best to answer them all. Our first question is from Praveen Wakode. The question is R1234ZE better than R134A? Mr. Saeed.
The R1234ZE is a new generation of refrigerants. It's called HFO. It has ultra-low GWP, which is 1, compared to the R134A, which is an HFC refrigerant and is having about 1,400 GWP. So this is the main advantage of the R1234ZE. The other advantage for R1234ZE, it provides a wider operating map. So yes, in general, we see now shifting in the world from moving from HFC refrigerant to the HFO refrigerants, including the R1234ZE. I hope I answered the question.
Thank you. Our next question is from Dinyanish Joshi, and the question is, should all the screw chillers have oil separators, or what are the thumb rules?
Yes, any chiller which is using refrigerant and oil should have oil separator. because we want the oil to come back always to the screws. You know that as the screws are rotating, we need the oil to remain there to ensure that, to prevent the wear and tear between the screws, and also to ensure the compression efficiency and tightness of the screws. And the oil tends to leave along with the refrigerant. So we should always separate the oil from the refrigerant, and allowing the refrigerant to continue to the condenser and bringing back the oil to the rotors. Okay.
All right, thank you. Our next question is from Muhammad Taha Ali, and the question is how to select oil separator with highest efficiency, and how is oil separator efficiency specified?
Okay. Sorry. The efficiency of the oil separator, for example, it's the oil separator that we talk about is high efficiency separator, for example, 99%. And the oil separation, it happens as follows. As we see, the oil and refrigerant mixture comes to the oil separator, and there are two forces affecting the oil droplets. It is the dynamic inertia, which is from the refrigerant and the gas, which is carrying the oil with it and tends to take it, let's say, to the condenser. And then there is the weight of the oil. Now, in the oil separator, we allow the weight force on the oil droplets to overcome the dynamic inertia by the cyclone effort. So that will allow the oil to drop and to be collected, and the efficiency is 99.5%.
All right, thank you, Mr. Saeed. Our next question is from V. Sridhar, and the question is, do you recommend the fogging or cell deck pad in front of air-cooled condenser coil to bring down the condensing temperature? And what precautions? Sorry, do you want me to repeat?
Sorry, yes, again, please.
Okay. Do you recommend the fogging or cell deck pad in front of air-cooled condenser coil to bring down the condensing temperature? And what precautions to be taken for longevity of aluminum fins if we adopt the above strategy to conserve energy? And is it economical when you work on LCC? Did you get the question, or would you like me to repeat any certain parts?
I'm not sure I understood the question very well. I understood a kind of, let's say, vapor cooling, like adiabatic cooling, which is, let's say, using vapor. This is what I understood. I hope I understood the question right. I understood that he means that using a kind of water spray before the condenser to bring the temperature. This is what I understood from the question. And yes, in many applications, it has been used, especially in the high ambient applications in the summertime. And it virtually reduces the ambient temperature and reduces the power consumption of the chiller. But of course, on the account of using some water. What precautions to take is to use the pre-coated aluminum fins. Sometimes we have pre-coated aluminum fins, coating for the fins, and to control the quality of the water which is used in the spray.
Okay, Mr. Sridhar, if Mr. Saeed has not answered your question, then please rephrase the question for us so we can re-ask. Next question is from Mr. Rami Tarabai, and the question is, can we add the heat recovery unit to an existing chiller?
To an existing chiller. I need to check actually for that one, because I can check with our service department if a retrofit can be done for an existing chiller to add the heat recovery option. So he can contact me at my email, which is mentioned here, saeed_allaham@shrine.com. I don't have a direct answer for that. I need to check with our service department.
All right, thank you, Mr. Saeed. The next question is from Mr. Muhammad Taha Ali, and the question is, wouldn't liquid heat recovery be more beneficial than de-superheater because of increased subcooling?
Sorry, again, the question again, please.
Wouldn't liquid heat recovery be more beneficial than de-superheater because of increased subcooling? Would you like me to repeat?
Liquid heat recovery. I don't understand what he really means by that one. the heat recovery is efficient. We have to, the total heat recovery, of course, is more efficient. Maybe he means the same as total heat recovery compared to the partial heat recovery. Maybe he's referring it to the liquid heat recovery. So if this is what he means, yes, because as we see here, the total heat recovery gives better efficiency than the partial heat recovery.
Okay, Mr. Muhammad, if you'd like to rephrase your question, if it hasn't been answered, please do so we can re-ask. Thank you, Mr. Saeed. The next question from Mr. Rami Tarabai is, what is the best method to check the performance of an existing air-cooled chiller?
Is the power consumption versus the cooling capacity to check the energy efficiency versus the original parameters. So the best way is to check, to measure the power consumption of the chiller.
Okay, thank you, Mr. Saeed. The next question is from Mr. Ahmed Labib, and the question is the heat recovery increasing the lift on the compressor, consequently reducing the performance of compressor and lifetime?
No, it does not affect the compressor. And the partial heat recovery is not a controlled process. It just uses the superheated gas. We get the desuperheating, and the rest of that one goes to the condenser to be spun, so it does not affect the compressor. In the total heat recovery, it can increase the efficiency because if the heat recovery brazed heat exchanger is bigger than the air-cooled condenser, it can lower the condensing pressure and minimize the power done by the compressor, but it does not affect the compressor.
Okay, thank you. The next one is from Mr. Osman Adra, and the question is, what about the problem of cross-contamination with Legionella? Is there any risk there?
For the Legionella? No, I don't think so. The Legionella, normally it's a risk in the static water, not in the moving water. So this is why it's always there is measure in every building where you have the water storage and the hot water storage is to increase the temperature and to treat the Legionella. So Legionella is not a risk here at all in the heat recovery on the heat pumps. Because the Legionella has to be treated anyway in the water tanks, in the hot water tanks, by increasing the water for that one. So that's not a risk. Actually, it's just a method or technology to help also overcome the Legionella.
Okay, thank you, Mr. Saeed. The next question, I believe, is a follow-up to the previous question from Mr. Dinyanish Joshi. The question says, R1234ZE is rated to be A2L. Should the chillers and other electrical components rated for mildly flammable refrigerants, should they be ATEX rated?
It depends about the classification. For example, as per ASHRAE A2L, yes, it's slightly flammable, which is okay for the air-cooled screw chillers. In Europe, they don't consider it flammable at all. So yes, it is A2L, but as we mentioned, like in Europe, it's not considered flammable. A2L is also acceptable to be used in the chillers.
Okay, thank you. From Alejandro Falcon Bonilla, the next question is, what about using heat recovered from chillers for space heating? Is it stable?
Sorry, question again?
What about using heat recovered from chillers for space heating? Is it stable?
Stability of the heat for the heat recovery, right? Yes, it is stable.
Okay, thank you. From Laurent Gallinet, the question is, can you please explain again the difference between the flooded type and falling film type evaporator? Okay.
The flooded type, it used a ball valve, so it was flooding the shell one third of the shell was flooded with liquid refrigerant, 2/3 is vapor. So that's the flooded type evaporator. The falling film evaporator, it uses electronic expansion valve, so it expands the refrigerant by electronic expansion valve in the shell. So using the electronic expansion valve to do that, we can achieve the high heat transfer efficiency, which is very similar to the flooded type. and at the same time not using so much refrigerant. So we are using smaller refrigerant charge in the falling film evaporator. So this is the difference between them: the use of the electronic expansion valve, while in the flooded type is using of the ball valve for the control.
All right, thank you. The next one is from Fadi Altora, and the question is the water heating system which is added to the chiller advisable to use?
Yes, absolutely. Actually, whenever it is possible, this is why we recommend, because this is an opportunity to improve the total energy efficiency of the chiller and the whole system of the building. And it doesn't have any negative consequence. On the opposite side, it has good opportunity to improve the energy efficiency. So yes, it is advisable.
Okay, thank you. The next one is from Vishnu Kakadavath, and the question is, why did the chiller cooling capacity decrease during partial or full heat recovery? And does heat recovery negatively impact chiller performance even though we have attractive TEER?
This is because I used a real computer selection to see that one. So because here the condenser will also affect the whole operation of the refrigeration cycle. So as we see, the changes was not that big. It was a little bit, right? Like it was not considerable, especially in the partial. In the partial, it was not, let's say, big change, considerable change, a little change. But as we said, because of adding heat exchanger in the condenser, it will affect the whole refrigeration cycle, and this is based on the actual selection coming from that. If we see also in the total heat recovery, the power consumption also dropped. So even, let's say, the cooling capacity decreased and the heat recovery increased, and the power consumption also decreased.
All right, thank you. The next question is from Rami Tarabai, and the question says, do you recommend using chilled water supply temperature reset based on outdoor air temperature as an energy efficiency measure in air-cooled chillers?
It depends on every project. I think this technique is used in many applications to reset the leaving water temperature by increasing the leaving water temperature and to minimize the power consumption of the chiller. Yes, this can be used sometimes, but we have to be careful about the impact for the comfort application and the air side.
Okay, thank you. The next one is from Muhammad Aboud, and the question says, please provide more clarifications about variable speed compressor and if it improves the efficiency or not, and what is the best compressor efficiency?
The variable speed drive does not improve the compressor efficiency. The compressor efficiency, the compressor is not running at one condition. It's running at different loads, different volume, refrigerant size, and also different pressures. At the full load, the compressor is running at the full load. This is the compressor efficiency. So what we know is we don't know the compressor efficiency. Normally, we know the chiller efficiency. And as we mentioned, let's say this is subject to many variables. So when we have more number of compressors per chiller, if I stop 1 or 2 compressors and I can run the chiller with 2 compressors out of 4, we have better control. So we try to run the compressor more near the fully loaded condition. Now, if we compare, let's say, the 2 methods for the capacity control of the compressor, which is the slide valve mechanism and the variable speed mechanism, the slide valve mechanism tends to be more efficient compared to the variable speed drive at high percent load of the compressor, such as 70%. At lower percent load of the compressor, if we say 30% or 40%, using variable speed drive will help to achieve the capacity control, but it will be more efficient compared to the slide valve. But for the overall efficiency, we don't look to the overall efficiency of the compressor. We have to look to the overall efficiency of the whole chiller, because the chiller has also condenser fans, it has electronic expansion valve. It's about also the mix of every component on the chiller.
All right, thank you. The next question is from Sankirt Santosh. And the question says, is evaporative cooling system effective for air-cooled systems?
Sorry, again, what is the question?
Is evaporative cooling system effective for air-cooled systems?
I think, yes, I think we got the same question before, which is, we call it, let's say, the adiabatic cooling, which is, it helps in, yes, it helps like in many projects where we have high ambient and we have high power consumption in the high ambient. Evaporative cooling can help to reduce the ambient temperature, and it can help reduce the condensing pressure and reduce the power consumption in the compressors.
All right, thank you. The next question is from Prakash Tasma. And the question says, is R1234, can R1234 work when outside ambient temperature is 55 degrees Celsius? What is the limitation on ambient temperature? And what is the discharge pressure at 55 degrees?
Yes, for air-cooled screw chillers, if we speak about comfort cooling, which is like chilled water temperature 712 and the ambient 55, yes, R1234ZA is working in that.
All right, the next one is from V. Sridhar, and the question says, can we use the shell and tube instead of PHE for producing hot water?
Yes, it can be used. We have to check, let's say, that, yeah, in principle, yes, it's a heat exchanger, so it can be used, yes.
All right, thank you. The next one is from Taqi-Din Sayed. And the question says, when the chiller is running at part load, what will be the impact if I'm using full energy recovery unit for heating purposes?
So if we have chiller with total heat recovery, what is the impact? This is the question, right?
If we have the chiller running at part load, what will be the impact when using full energy recovery unit for heating purposes?
Okay, so at partial load, yeah. So of course, the cooling capacity will be decreased and the heat recovery will be decreased at the partial load. Depends on the partial load.
All right. From Qasim Shahzad, in case of no load of hot water, what is the impact on partial heat recovery on the chiller?
This is why it's limited to 25%, so that even there is no load on the heat exchanger in the partial heat recovery, it will not have impact on the chiller because all of the surplus heat will go to the condenser. So all of that will be cooled by the condenser, by the air-cooled condenser.
Thank you. From Raouf Bokhtar, do you recommend using heat recovery units over central heating ones in terms of hot water supply?
Using heat recovery over what?
Do you recommend using heat recovery units over central heating ones in terms of hot water supply?
We recommend using the heat recovery in central hot water system in conjunction with other systems. So the hot water system cannot depend on the heat recovery alone, but the heat recovery can help reduce the energy consumption a lot. It can be used in conjunction in a central heating system with solar or with boilers or with electric calorifier, any other system. So it can be used along with that.
All right. From Mr. Muhammad Taha Ali, how is the greater than 99% efficiency calculated? Especially with VFD chillers, cyclone effect will not be enough at low speed. How to select oil separator for VFD chillers?
That's actually based on the constant volume, not the variable speed volume compressor.
Okay. From Prakash Tasma, is capacity control sliding valve type better or VSD from energy efficiency point of view? How much is the variation between them?
Yeah, as we mentioned, the higher percent load variable speed, the slide valve is more efficient. In the lower percent load, VSD may be more efficient. But as we mentioned, we have to look for the whole chiller. We cannot evaluate, let's say, one technology because there is the number of compressors per chiller is important, the condenser fans, the slide valve, and the variable speed drive, different techniques. What we need to look to is the overall chiller. So the total chiller from what is the IPLV for the whole chiller.
All right, thank you. From Sarfaraj Khan, can we add heat pump to an existing chiller?
To add a heat pump to an existing chiller, I have to check. It's something like project specific. So we need to look to the project specifications for that one.
All right, thank you. From Velraj Rajadurai, how efficient are modulating vanes in constant speed compressors?
Sorry, again?
How efficient are modulating vanes in constant speed compressors?
I need to check that question and come back again. So.
All right, thank you. From Hazem Abdelkarim, is twin screw compressor, do twin screw compressors have an advantage over single screw compressors?
Well, the twin screw compressor has two moving parts only. So as the less moving parts we have, the more reliable the compressor is. The single screw compressor, it has, single screw and two gate rotors, so it has three moving parts. The other thing is that the twin screw compressor is made from steel, so the twin screw is sized for the lifetime of the compressor, while the gate rotors is made from different materials, so it may need more service. So this is what I believe.
Thank you. From Mr. Magid Ayub, are these units effective to use in a swimming pool air conditioning and heating system?
Yes, smaller size heat pumps can be used for it's actually a typical application for using for the heating of the water for the swimming pools and heating application.
Thank you. From Mr. Alauddin Sweeti, what is the maximum temperature that we can get from the D superheater?
We can get temperature like 60 or 70 degrees Celsius for the hot water.
All right. From Magid Muhammad, which is better for screw chillers, DX or flooded evaporator?
We believe that the best one is actually the combination of both of them. The DX has its pros and cons, and the flooded has its pros and cons. And the one which combined the advantage of both was the falling film, which is having the advantage of both of them. We believe that this is the best one because it provides the lowest charge, refrigerant charge, and the highest heat transfer efficiency.
Thank you, Mr. Saeed. From Osman Adra, can you elaborate on the VSD controlled parts of the double screw compressors?
The control for the variable speed drive in the compressor, it controls, let's say, the frequency of the compressor. For example, for the company that I work for, I don't know how, for example, others are controlling the variable speed drive for the compressor. But as far as we are concerned, I know, for example, that we control the hertz from 50 hertz to 25 hertz. So the minimum speed of the compressor is 1,750 RPM, and the maximum speed is 3,000 RPM. And we use also at the same time the slide valve. So the microprocessor will send signal to the variable speed drive and also to the slide valve. Now it will control both in unloading the slide valve and the variable speed drive. So that will be in response to the cooling load, to the demand cooling load, which is based on the signal about, let's say, for example, the delta T between the supply and return water temperature.
All right, thank you. From Muhammad Bey, is falling film evaporator also flooded type?
No, it's not flooded type. because it does not flood the shell with a big charge of refrigerant. It only expands. So it's considered as hybrid of the flooded type and the DX.
All right, thank you. From Dia Derwish, what are the benefits of the ice storage in a chiller system, since the chiller is controlled to work as per the required load, and the compressors will stop after achieving the set point?
The ice thermal storage or any thermal storage, it helps sometimes, let's say, in achieving the peak and minimizing the of the chiller generation at the peak. So we can use the chiller in the night where the ambient temperature is less to make thermal storage, and that can be used in the day. So this is the advantage for it. And it makes more sense when the electricity tariffs are different. So if the tariff of the kilowatt hour is more expensive in the daytime, it makes also more sense. So it's a matter of efficiency and economy.
All right, thank you very much, Mr. Saeed, for answering these questions. Unfortunately, we've received a huge amount of questions, but now we've run out of time and we've reached the end of our session. We have, however, kept a record of all your questions, and Mr. Saeed will be answering them for you shortly, either by email or otherwise. So thank you so much to everyone that has attended today's webinar. We hope it was beneficial for you and that you've enjoyed it. Thank you so much, Mr. Saeed, for being our speaker for today. We have an upcoming webinar coming on next Sunday, and we hope to see you there. Thank you very much. And goodbye.
Thank you.